Ever wondered how your phone or smart device can run AI models so quickly without draining your battery? It's not magic, it's smart math. Today, we're breaking down a breakthrough called BlockFFN, a game changer for making AI faster and more efficient, especially on devices that can't handle supercomputers. Let's start with a simple question. Why do AI models take so long to process text? Imagine a library with millions of books, but every time you ask a question, the system checks all the books, way more than you need. That's what happens with traditional AI models. They activate every part of their brain, even if most of it isn't relevant. It's like using a sledgehammer to crack a nut. But here's the twist. AI models have experts, specialized parts that handle specific tasks. The problem? Most models can't choose which experts to use. They either activate all of them, slow and wasteful, or a random few, which might not work well. This is where mixture of experts, MOE, comes in. Think of it as hiring a team of specialists. If you need math help, you call the math expert, not the chef. But there's a catch. Even if each word in a sentence only needs a few experts, traditional MOE models still end up activating way more than they should. This is called low chunk level sparsity, like having a team of experts, but they all show up for every meeting, even when they're not needed. So how do we fix this? The BlockFFN team tackled two big problems. 1. Rigid routing. Current models can't adaptively pick the right experts. 2. Low chunk level sparsity. Activating too many experts slows things down. Their solution? A smarter router that uses ReLU, a math trick that lets the model decide how many experts to use, and RMSNorm, a technique that balances activation strengths. It's like giving the model a flexible checklist that updates in real time. But here's the real magic. BlockFFN improves chunk-level sparsity. Imagine processing a paragraph of text. Traditional models might activate the same experts for every word, but BlockFFN ensures that each chunk of text uses only the necessary experts. This is achieved through two key innovations. Activation locality loss teaches the model to group words that need the same experts, like recognizing patterns in a recipe. Chunk sparsification loss directly targets efficiency across entire blocks of text, not just individual words. The result? Over 80% token-level sparsity, most experts are idle, and 70% chunk-level sparsity. It's like organizing your library so you only grab the shelves you need, no more sifting through useless books. Why does this matter? It means AI models can run faster on devices like smartphones, smartwatches, or even IoT gadgets. Think of it as making a superpower accessible to everyone, not just data centers. BlockFFN also shines in speculative decoding, where the model predicts future words to speed up processing. By combining sparsity with this technique, it skips unnecessary computations, like skipping entire shelves in a library. Now let's dive deeper. How do you teach a machine to be selective? Imagine you're baking a cake, but instead of using all the ingredients in your pantry, you only grab the ones you need. That's sparsity, this superpower that lets AI models work smarter, not harder. But how do you teach a machine to focus? AI models are like hyperactive chefs. They have tons of tools called experts to tackle tasks, but if they use everything at once, they get confused and slow down. Researchers tested mixture of experts, MOE. Think of it as assigning specific chefs to specific parts of a recipe. But how do you decide which chefs to use and when? That's where activation functions come in. They're like the recipe's step-by-step instructions, telling the model when to turn on certain experts. Here's where it gets wild. The team ran experiments to see what works best. They tried spreading work evenly across all experts, like juggling 100 balls at once. But that backfired on devices with limited power. It's like trying to cook a gourmet meal with a toaster oven. Nope, it doesn't work. Instead, they found that keeping related tasks close, what they call activation locality, was way more efficient. It's like grouping similar ingredients in your kitchen. Everything's easy to find, and you don't waste time digging through drawers. To fine-tune this, they built an adaptive factor scheduler. Think of it as a thermostat for AI. It automatically adjusts how many experts the model uses based on the task, like dialing the heat to keep your house just right. And the results? They hit a sweet spot with 40 experts. Too few, and the model's too simple. Too many, and it's chaotic. 40. That's the Goldilocks zone for efficiency and accuracy. Here's the kicker. They also boosted speed with acceleration kernels, like giving the model a turbo button. One method, hours 32 talk, made text processing 4.68 times faster on some tasks. How? By optimizing speculative decoding, a fancy way of saying the model guesses the next word smarter. But here's the catch. This speed boost isn't a magic bullet. In tasks like translation, where the text is tricky or short, the model sometimes guesses wrong. It's a trade-off between speed and precision. Oh, and one more twist. Models with gated experts, think of them as router systems that pick the best chef, actually performed worse. Why? The router and experts ended up competing for resources, like two chefs fighting over the same pan. So the simplest approach, non-gated experts won out. So what's the takeaway? AI isn't just about raw power, it's about smart, efficient design. By balancing focus, speed, and adaptability, researchers are paving the way for AI that's not just fast, but wise about how it works. Thanks for watching. Drop a comment if you're curious about how this applies to your favorite apps. Stay curious, and we'll see you next time.